Now that we've covered series circuits, we can finally start talking about parallel circuits. So unlike series circuits where there's one path from start to finish of a battery, a parallel circuit has multiple paths. So as you can see in this picture here, you have more than one loop around your circuit that you're able to travel through. If you're able to take your finger and trace along your circuit where there's more than one path, that's a parallel circuit. If you think about Christmas lights or holiday lights that you may hang on a house or a tree, those lights, if one light blows out, well, it would be a real shame if they all went out, right? So those lights are not connected in series, those are connected in parallel so that you're able to have multiple paths that the current can take. So a parallel circuit is a circuit in which all of the resistors are connected in parallel to the same voltage source. In other words, they're all connected parallel to each other connected to the same battery voltage source, not sources. Okay. The charges fall through the larger resistance at a slower rate. Less current flows through that branch of the circuit. Current and charge relate to each other. The total current flowing into and out of the battery is the same. Okay, so when we talk about parallel circuits, we are looking at the parallel circuit rules, which is found on page 4 in your reference table. If we're talking about solving for your total resistance, the inverse of your equivalent resistance is the sum of the inverses of each resistance. So 1 over Req, I'm going to write this a little bit different so that way you can see it as an actual fraction. So you have 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3, all the way up to 1 over Rn, where n represents the total number of resistances that we have. The total current in the circuit is equal to the sum of the current passing through each resistor. So your total current is equal to I1 plus I2 plus I3 plus all the way up to In. The voltage is the same for all resistors in the circuit. So V1 is equal to V2, which is equal to V3, which is equal to all the values that you have up to the total amount. In a series and a parallel circuit, you should notice already that you have some changes, you have some differences. So when we were talking about series circuits, we talked about the fact that current was the same everywhere. You had one path to take. Here, in a parallel circuit where there's more than one path, you do not have current being the same. Your current is going to be split among the different paths that you will take. The voltage is the same for all resistors in the circuit. In this case, where you have one battery, that voltage is going to be equally supplied to each resistor, unlike a series circuit in which your voltage had to be added among each resistor. All of your components in your circuit, just like when we talked about series circuits, and the whole circuit obey Ohm's law, which again is V equals IR. So just like we set up our chart when we did series circuits, we're going to do the same thing for parallel. We just have a couple of different rules that we're going to use. As far as the junction rule, we're going to talk about that tomorrow. So I'm going to hold off for that, and we're just going to jump right into doing some problems here. So This is what a parallel circuit looks like. Again, you have more than one path that you're able to take as you go from a battery. So as you travel out of your battery right over here, let me get a different color so that we can see what's happening. So as you travel out from your battery, you're able to go around this way, or you could have, we'll go a different color, we could have not turned down R1, we could have traveled all the way around and went around R2. Or we could have gone ahead and we could have come out of our battery and traveled all the way around to go to R3. So in this case, we have 3 loops, 3 resistors. These are all parallel to each other. We know that parallel do not intersect. So these resistors are parallel to each other, and we have a circuit that looks like this. Okay, so to solve for this, we're going to do the same thing that we did before. We look to see what we can add into our chart. We look to see what kind of rules we can use. So the first thing that we have here, we have all of our resistors listed, but we have to make sure you're using the correct formula. So now, if we are solving for REQ, the formula that we have on our reference table looks like this. We have 3 resistors here. Again, remember, this R4 really is REQ. It's just your total resistance. So we have 3 total resistors. So here's our formula. In order to solve for this, we go ahead and we write down everything we have. So 1 over 30 plus 1 over 30 plus 1 over 30. No, your resistors will not always be the same. It just so happens that they're the same in this case, but they definitely will be different. So we have 1 over 30 plus 1 over 30 plus 1 over 30. Okay, if we solve for this, this means that 1 over REQ is equal to 1 over 10, if you do this correctly in your calculator. Now let's talk about your calculator for a second. So we're adding fractions here. You cannot just type in 1 divided by 30 plus 1 divided by 30 plus 1 divided by 30. You have to make sure when you're putting in your calculator, you are using parentheses around each fraction so that you end up with 1 over 10 as your answer. However, if you look to see what we just solved for, we solved for 1 over REQ. And we don't want 1 over REQ. We want to solve for REQ. In order to do this, we can do this 2 different ways. We're able to either take the inverse of our fraction, or we can do 1 divided by our answer. So this is what I mean by that. We are able to take this to be able to solve. We can do either, the choice is yours, 1 divided by 10 raised to the negative 1 power. That's taking the inverse. We could also do 1 divided by 1 over 10, which is also doing the inverse, but just using fractions. Again, the choice is yours. You can either do one or the other. You should get the same exact answer for both. This happens to be a pretty easy one because if you do 1 divided by 1 over 10, you will end up with 10 as your answer. You will definitely not always have really nice numbers like this. You will be working with fractions, so you do have to make sure you know how to put this in your calculator. This definitely you need to make sure that you practice because you have to make sure that you're putting in your fractions correctly. One of the things that you should also note when you're looking at this, your total resistance in a parallel circuit should always be less than each individual resistor. So what I mean by that is REQ should always be less than each 1 over each R1, R2, R3, R4, and so on, because you're talking about fractions. So if you're talking about a fraction, your total value should always be less because it has to be in a fractional amount. Okay. Once we have this, everything else really is self-explanatory. The hardest part of parallel circuits is just doing this fraction part. Otherwise, everything else should be okay. So now we can go ahead and we can calculate our I using V equals IR. So we can go ahead and we can, actually, let's extend that over here. So we can go ahead and we can do that. So V equals IR, 60 volts is equal to I multiplied by 10 ohms, we end up with I equaling 6 amperes for our total. If we go back and we look at our, if we look at our parallel circuit rules, we see that in a parallel circuit, your voltage is constant everywhere. Don't make the mistake and switch it with series. So if my voltage is constant, then I know that my 60 volts is going to be for each one of my resistors. I could then go ahead and I can solve for all of my unknown currents using V equals IR. So again, if I want to solve for R1, I can solve V equals IR. I have 60 volts is equal to I multiplied by 30 ohms. I should be equal to 2 amperes. Now, because all of my resistances happen to be 30 for this problem, I can go ahead and I can skip the math, and I know that all of my currents have to be 2 amperes because my resistors are all the same. Again, this is solely for this problem. The numbers happen to work out this way. It will not always be equal. You do have to do the math. As far as the power goes, we'll say the same thing as we did before. Power, you guys can solve for this. So we have P equals IV. You could solve for V squared over R, I squared times R. The choice is totally yours. If we solve for this here, we have 2 amperes multiplied by 60 volts. We should end up with 120 watts as our answer for the first. If you go through and you solve for the rest, again, all of our values are the same. So avoid the math, realize what's going on, and we can just write it in. Our total should be 360 watts when we add them all together. For this one right over here, again, we have a parallel circuit. We know that because there are multiple paths that you can take. They list here for us all of our resistors. The difference with this picture and a series circuit is now your current is specific to that resistor. So this right here, this is an ammeter. We know it's an ammeter not only because we have 0.05 amperes, but because it's on your circuit, on one of your wires connected to your resistor. The question is, which resistor is this current going to be associated with? So as we go through and we look, if we follow with, you take your finger, literally trace around it, that wire is connected to your R3, which means that that 0.05 amperes is representative of the 0.05 amperes flowing through R3. So we can go ahead and we can label that right here. At this point, you have a couple of choices. You can go through, you can solve for your total R, you can solve for V. I'm going to solve for V first. So solving for V first, we're able to go ahead, solving V equals IR. V is equal to 0.05 amperes multiplied by 50 ohms. We solve for V to be 2.5 volts. So 2.5 volts flowing through our 50 ohm resistor. We know that voltage is the same for all of our parallel circuits. So 2.5 volts going through R1, 2.5 volts going through R2, and our total REQ being 2.5 volts in our circuit, which means that our battery, this right over here, is 2.5 volts of potential difference. Okay. At this point, again, you have a couple of options. You could solve for your resistance. You could solve for your current values. Again, the choice is yours. Let's go and solve for resistance so we can practice with these fractions here. So if we go ahead and we do that, we are solving for 1 over REQ, which is equal to 1 over R1 plus 1 over R2 plus 1 over R3 because we have 3 resistors. Solving using parallel circuits is usually a part 2 on the Regents because this is a little bit more complicated than that for a series circuit. Series is definitely more straightforward. You don't have to worry about fractions. So this is the one they usually put on the Regents. And you need not worry because you will be totally fine. So we have 1 over REQ equals 1 over 70 ohms plus 1 over 60 ohms plus 1 over 50 ohms. 1 over REQ is equal to 1 over, do not round, write out the entire number. You should have ended up with 0.0509 ohms. What happens is if you round, you're prematurely rounding your answer. So you don't want to do that. You always want to either utilize the answer button on your calculator or write out the entire number. Okay. So now we want to solve, and we want to solve for REQ. We don't want to solve for 1 over REQ, so we have to take the inverse of this. Again, the choice is yours, whether you want to raise it to the -1 power or you want to do 1 divided by your answer. Again, whatever you prefer. This time I'm going to go ahead and I'm going to raise this to the -1 power. So in your calculator, you literally are copying exactly what you see. Parentheses, 1 divided by 0.0509, close parentheses, raise it to the -1 power. Be careful you're not pressing in the subtraction sign. -1 is not -1. What? I'm plugging it into my calculator. Hold on. And why am I not getting the 1 divided by 0.0509? What? One divided by 70 plus 1 divided by 60 plus 1 divided by 50. Okay. So I'm leaving this in. I'm not going to restart this because I think it's important that you see the kind of mistakes that can be made here. And I definitely just made one of those mistakes. So I went ahead and I was raising this to a power that was already raised. So let me start from here so that we can kind of go through and see what's happening. Okay, so if you go ahead and you solve for your answer here, solving for 1 over 70 plus 1 over 60 plus 1 over 50, you should end up with not 1 divided by, you should end up with 0.0509. And I actually did round that. So we don't want to do that. So 0.0509, 5, 2, 3, 8, 1. Again, you don't want to prematurely round anything. We want to take the inverse of this value because this is the one that we want to get rid of. So we'll take that and we'll raise that to the -1 power. There we go. And if you did it correctly, and did not make a mistake like I definitely did the first time, you will end up with 19.62 ohms. So that means that this is 19.62 ohms for my resistance, my total resistance. Again, this total resistance should be less than each individual resistor. And just to clarify one more time, because I got confused for a second because I was making a math error as I'm telling you not to make the math error. But as I went through, I basically did like a double inverse of my answer. And that's why it's so important to be writing out everything and not trying to just do it all in your calculator. Somebody who's good at math, like myself, definitely can make mistakes too. So just be careful, go slow, and you definitely will be okay. Your last step here before going through and worrying about power would just be to solve for V equals IR for all of these missing currents here. If you do this and you do this correctly, you should end up with 0.036 amperes, 0.042 amperes, and your total to be 0.28 amperes. If you go through and you solve for your power, which I know you can do, here I got 0.09 watts for R1, 0.11 watts for R2, 0.13 watts for R3, and 0.32 watts for your total power in your circuit.